This first lecture is very much an introduction. It's an overview of where we're coming from and why. So I see people in the audience who I think know all this. So there's different levels in the audience, and we'll try and do it. The second thing I want to say is Aviv and I have slightly different ways of doing this. I tend, when I give lectures also in class, to hand out a full lecture. I can't tell if I do that just because of my own insecurities or because I think it's good, but the advantage of it is my students come back afterwards and say, well, what I didn't get in the lecture, I can read through the notes, the whole thing. The disadvantage of it is there's a lot of stuff on the board, okay, because it's exactly what you have in your hands, what's going to be on the board, okay? That's too much on the board at once, so you're going to have to listen to me, but if you just, you can write down easily one or two things and then come back to it. The reason I do it this way is my students tell me that afterwards, they find it very useful afterwards to go back to the notes and be able to read through them, okay? But that makes the lectures a little problematic. Okay. So we're going to be interested in the analysis of demand with differentiated products, and we'll look at some of the implications of that for markups and profits and for price indexes and hedonic regressions, which are all sort of directly related to that, okay? And what I want to start with is why are we so interested in that, okay? So the demand system essentially embodies much of the information you need to analyze the incentive-facing firms in a given market, okay? So the two types of incentives we usually deal with immediately in I/O, and sometimes more, are pricing decisions, okay? And the incentive to invest in alternative types of investments, either capital, R&D, or advertising, okay? So if you were going to look at the response of either prices or investment decisions to a change in the environment or in a policy, okay, the incentives facing you would be coming from the demand system largely, okay? Now there are actually two or three other components of the decision-making process which you would actually do. So if you were going to recompute a static equilibrium after a merger, say, okay, you would need a demand system, you would need a bunch of cost systems for the various people, and you'd need an equilibrium assumption. Okay, essentially that's what would go on. Okay. The demand system is the thing we typically have most data on. Okay. Cost data is generally proprietary. Okay. That's not true in regulated industries, but in most industries it's generally proprietary. Worst with in I/O. We use it in Nash and prices or something else, and I'll show you why we use it. Because it works out being a good approximation. Okay. And that approximation is good enough for certain things, and it isn't good enough for certain other things. Okay. But in the end, you're going to end up relying a lot on the demand system because the pricing assumption will just be Nash and prices. And the costing and the cost system, often because you don't have data on cost, you will derive it from the Nash and pricing assumption. You will just figure out what the cost must have been to set prices equal to the prices that we saw prior to the merger or prior to the tax change or prior to the environmental change. Okay, so the demand system ends up being probably the most important piece of tool that you're going to use when you do any of these analyses, okay? So that's the main reason. The other reason is welfare analysis. So the way we're going to work these modern demand systems is we're going to work from individual utilities, okay? So we start with an individual utility function. We have a distribution of those utility functions across agents, and then we're going to explicitly aggregate up to get market demand. Is that clear? So if you were going to analyze welfare, okay, you could actually use this system to analyze the distribution of outcomes to different people's utility, or the distribution of consumer surplus that this policy or this environmental change or decrease in consumer surplus that the policy or the environmental change did. Okay, so that ends up being important for all sorts of issues. For example, if you want to find out the benefits to consumers of new goods, okay? You could do it that way, okay? And that's the kind of thing that underlies, we'll go back to that question, that particular question. It underlies much of the policy towards R&D activity, okay? If you were going to analyze the outcomes of regulatory policies, you'd want to know the whole distribution of impacts across consumers for two reasons, really. Often because the regulatory policy itself is directed at changing consumer benefit or different kinds of consumers' benefits. and also for reasons that the regulator is typically either an elected official or appointed by an elected official, okay, and he will be sensitive to the distribution of consumer outcomes from the policy that he does, okay? And then there's going to be the construction of price indexes, okay, like the CPI, and it's used for a multitude of things in the economy. It's used for indexation programs, tax brackets, government salaries, and the like, okay? So if you actually figured out how to, there was once, we'll get to this, but if you actually figured out that the CPI overestimated the cost of living index by 1% in something like 10 years, you solve the budget deficit problem. Okay, it's not a small number, okay? Okay, so I'm going to now take a step backwards and say where we're coming from, okay? And then I'm going to go to where we're going to, okay? So typically there's been two breakdowns of demand systems in the literature, okay? One set distinguishes between representative agent models. There's a single agent with a single utility function. We derive demands for that representative agent, okay? And the other set is heterogeneous agents, okay? So that's one breakdown, okay? And the other breakdown is going to be that we're going to do demand directly on product space. So there's going to be a demand function for each product as a function of the prices of all products, okay? So that's product-based demand systems, and what I'll call characteristic-based demand functions, which is the utility from a product just depends on its characteristics. There's no, if I knew all its characteristics, I know the distribution of utility that comes from it. Is that clear? And the demand function, we're going to change the space. The demand function will be on tuples of characteristics or on vectors of characteristics. Okay? So that's where we're going to end up. But I want to talk a little bit about the product space and why we ended up there. So you'll see the product space stuff is still good for some things. Okay? It just doesn't work out to be good enough for many of the I/O applications. It just can't handle it. Okay? So these are the demand systems that are been in the literature for a long, long time, the first demand systems ever in economics. Okay? Typically, they were applied in representative agent models, not in heterogeneous agent models. And that's sort of historical. When we started using demand systems in economics, you couldn't actually aggregate up over a bunch of people and get the aggregate demand system and do it on a computer. The computers just weren't good enough, okay? So we had a representative agent, and the assumptions you needed to go to aggregate, there are some assumptions that allow you to aggregate explicitly into an analytic form that I could take for a demand function. So there'd be a distribution of utilities, and we'd sum over them, and there'd actually be an analytic form for the outcome. Okay? But they ended up being extremely sensitive to the distributional assumptions and very hard to use when you're using the actual distributional assumptions in the population at large. For example, the one thing that probably the most important differentiation between consumers for price effects, which we're always interested in, is income distributions, okay? So you'd want to mimic the income distribution when you aggregate it up, and it ended up being very hard to do that, okay? So I'm going to start with this little digression. This is no longer a problem in economics, okay? Even in either product space, we're going to use it in characteristic space, but either product space or characteristic space, okay? It's just not a problem anymore. It's because of the advent of computers and simulation estimators. Okay, so I'm going to do this this is a small digression. I'll do it quickly, but it will tell you why we should always be doing heterogeneous agent models. Okay, so I'm going to let Z denote the consumer characteristic that differentiates the different consumers' utility functions. So it might be family size, income, a lot of things, okay? And at least the demographic components of Z are usually available to us from something like the CPS. Okay, so this is not a data problem. Okay? We may not be able to match individuals to the products they bought, but we know the distribution of individual characteristics from the CPS. Okay? And so we're going to have a model for individual utility given its characteristics, the price of the product of interest, and the price of other products, which is P minus J. And some parameters which will determine the interactions between characteristics and preferences. Okay? So then the aggregate demand is just the integral, or the sum over everybody's utility will generate for them a quantity, this quantity for individual with characteristic Z, and then the way you'd get aggregate demand, you just sum out. Okay, so when I put down an integral, you can think of sum, it's fine, I don't care. Okay? So it's easy enough now to calculate this with modern computers, okay? So it's just not an issue. What you do is you take NS random draws. You just take random draws from the CPS, okay, or from the distribution in the CPS, okay? Each random draw, okay, is a Q. It's a random draw on a Z. It's a Q, okay? So for that theta, I can tell you what that Zi would do. Okay, that's what the utility function tells you. If this is my Zi and these are the prices, and we have the parameter vector, the utility function will tell you what he will buy or how much of what he will buy. Okay? Then you then just add up. So for every random draw, you add up, okay, over the quantities bought, and you divide by NS, so that gives you an average of these people. Okay? And so that's your estimate of the demand at that theta vector. Okay? So if E is the expectation of that, the expectation of any one of these, it's a random draw from that distribution. So the expectation of any one of these is exactly the right thing. Is that clear? And the variance goes down like 1 over NS. Okay? So I can get an unbiased estimate with as much precision as I like by increasing NS sufficiently. Is that clear? So there just isn't a problem with doing heterogeneous agent models anymore. It's a little bit of computer, but with modern computers, this is like milliseconds. Okay? It's just, there's nothing to do. Okay. So I'm going to argue that even if you were going to work in product space, again, I probably should have two sets of things, a bunch of points for the lecture and then a handout. But I'm too lazy to do that, so you just get a handout. Okay. So there are really, even if we stay in product space, and we're not going to stay here very long, okay? I would argue that with modern computers, there's really very little excuse not to do heterogeneous agent models anymore. And there are two very good reasons to do them, okay? One is you can combine data on different markets and or time periods in a sensible way. So if you had market level data, which is a typical thing, say you're going across counties in Connecticut, okay? So we know, the one thing we know is that the impact of price depends on income, okay? People with low income or low wealth of other kinds, okay, care about price more, okay? You want to combine data from different markets. So I don't know, we're in Connecticut, we're doing counties, and there's Greenwich where all the guys from Wall Street live, and there's, I forget the name of the city that just went bankrupt, starts with a B, Bridgeport, okay? The distribution of income in Bridgeport and in Greenwich are very different. You should expect to get very different price coefficients in those two. And if you just put all the data together and assume a representative agent, it's not clear what you're doing. Whose price coefficient are we estimating? Why are we estimating it? Why should they be the same in the two cities? Is that clear? Whereas it's very easy to do this once you have your model and let the income take care of it, okay? And the other reason to do it in heterogeneous agent framework is because often we really do want the distribution of responses, particularly from government policies, by the way. Okay. So this table was designed to convince you of this. Maybe the Bridgeport example, Greenwich example did, but this is a table of counties across the United States, and you can see that this is the fraction, the average fraction of people in the 0 to 20,000 range. I forget, this was done in 2004, so it's probably about 2001 data. And if you go down here, and here's the variance across counties in those proportions, and you can see particularly in the high income groups, okay, where most of the products are directed, okay, the coefficient of variation is about 1. So there's that's a lot of variation, okay, in proportions with different income classes across different counties. Okay, so it would make it very difficult to aggregate without something that allowed for the heterogeneity of the different counties. Okay. Okay. So now we're going to stick with heterogeneous agent models, but even if we stick with heterogeneous agent models, there's still a question whether we want to do product space or characteristic space. I'll tell you now. I'm going to start with what happens in product space, okay? And I'm going to tell you why we don't use it that much in I/O anymore, although in cases where these problems don't show up, you might well use it. There's no reason not to, okay, as long as you're careful when you use it, okay? And then I will go to characteristic space. Okay. So whatever we do, whether we start with product space or characteristic space, we're going to start with an individual consumer's utility function, okay, and then derive the quantities that the individual does, and then aggregate over people. Okay, so I'm going to start with the individual consumer demand function or utility function. Okay. So when you use product space from the point of view of markets, okay, differentiated product markets, you end up with this too many parameter problem. So let me explain what happens. If you're doing demand between capital J goods, okay, so you're going to have a quantity on one side for each of the goods, okay, and you're going to have the price, even if it's only log linear or linear, you're going to have the price of each good on the right-hand side, okay? So that's J coefficients on the order of J coefficients for every good, and if you have J goods, that's J squared parameters you have to estimate, even if it's only linear. Is that clear? Okay. So it's not unusual to have over 50 products in a market that you're doing differentiated product analysis with. Indeed, the auto examples that Aviv's going to come up with, one of the sets had 100 products, the other had 200. So even if it's just 50, 50 squared is 2,500. There is no data set that's going to allow you to estimate 2,500 parameters, okay, with any precision at all. Okay, so that's called what we call the too many parameter problem. I don't know what the official title is, but it's the problem that's moved us into characteristic space, really. Okay, the other problem with doing it in product space is if you're trying to analyze a market, one of the questions you want to ask typically is, what would be the demand for a new good? Is that clear? And you can't do that in product space until the new good's already out. Is that clear? Because there's just no information in the data on it. If you have characteristic space, we'll come back to this, there's things you can do. Because you can ask, you know, I now have a distribution of preferences over different characteristics. If I put in a new set of characteristics, what would happen? Okay? Because there's information on preferences over tuples of characteristics, and it will have some information on the characteristics that you put in. Okay? So those are the two real reasons that we move to characteristic space, and we'll come back to it. The first reason, by the way, underlied a lot of historical work on demand systems. So everybody knew this was a problem. We weren't the first people to say it was a problem. Okay, and you know, there were various ways around it. There was the Hicks composite commodity theorem, which just said, I'm going to assume that all prices move in proportion. Okay, so that's what and then you can get a demand system with, you can collapse the demand system. But that doesn't allow you to analyze substitution between products. It just allows you to look along an expansion path. Okay. Similarly, there's things like CS preferences. Okay. CS preferences means that any two goods are equally substitutable for each other. Okay. So you can't really analyze competition between goods in a market, okay, because they're all equally competitive to each other. Okay. Also, it has very funny welfare implications. So Aviv will get to that. Worse than the Logit implications, which are bad enough, the pure Logit. So those we ruled out automatically. The one that actually got some bite in the literature is Gorman's polar forms. This is multi-level budgeting. Okay. So the idea in multi-level budgeting is pretty simple. You first allocate expenditures to groups of goods, okay, and then you analyze within each group separately. Is that clear? So I know how much money I'm going to allocate to cars or to something else, okay, and then I'm going to have to do the demand for individual cars within that budget allocation, okay. To do that, you need two properties. One is you have to have what's called weak separability. So what happens in there is that the purchase or the prices for goods in one group have to have exactly the same impact on the goods in the other group, because these are sub-utility functions for vectors of goods. Okay, so the cross effects can only come through the effects on these V's. So there's a contribution of V to here, but the cross effect between V1 and Vk, between the goods in 1 and k, okay, these are grouping things, have to be exactly the same. Okay? And then the second thing is you have to be able, so that allows you to substitute down and do each one of it separately, given their budget. Is that clear? Okay. And so the second thing you need is you need to be able to form a price index for the budget group. Okay? So what Terence Gorman did, was he gave necessary and sufficient conditions for these things to be true. Okay. the only things that work, so these are necessary and sufficient, so it's an if and only if statement, okay? Is weak separability, the separability between these bundles of goods, and constant budget shares within a group, okay? Or strong separability, which is additive utility. One group is added to the utility of another group is added to another group, and then it doesn't have to go, the budget shares don't need to go through the origin, but they still have to be a straight line, okay? So this is what happens in the almost ideal demand systems, okay? So this is all in the way of background, okay? But if you see almost ideal demand systems, that's essentially what they're analyzing, okay? So groups have to have this, you have to have, every good has to have the same income expansion path, okay? Which we don't think is true, and the groups have to satisfy this weak separability condition. So, I mean, you can think about doing this, and if the sets aren't very disjoint, okay, if you don't have too many sets, you'll find out that it's going to be very difficult to do it, because there are expensive small cars, okay, and there are inexpensive large cars and expensive large cars, and so you'll have to start splitting them out. If you wanted to do VERs, you wanted to do something that had to do with imports, you'd have to also split out the goods that came from Japan from the goods that came from the United States. They'd all be separate groups, okay? And you'd have to assume that this characteristic, that there's no cross-price elasticity between the groups. So they're hard conditions to meet, and actually they're going to reappear a little bit. The other problem with them, by the way, is it's very hard when you have a continuous characteristic to start splitting it up into groups, okay? And the continuous characteristic of most interest to us is price. Is that clear? Price is distributed continuously, and you cannot separate it out into group, you'll see, because in demand systems there's going to be an error term, and it's going to be correlated with price, typically, okay? So if you started separating it out between high-priced goods, low-priced goods, you'd get the error term selected, okay? And you'd have a selection problem on top of everything else, okay? This, by the way, goes with all grouping procedures, nested logit, as well as, the almost ideal demand system, okay? Those problems are going to reappear. Okay, characteristic space. So that's background. That's why we are where we are. And I'm going to give you a short introduction to characteristic space now. So we're going to treat products as just bundles of characteristics. So if I know the characteristics of the product, okay, I know the utility for the product, okay? Now these characteristics, some of them will be observed, but we're going to allow for unobserved characteristics also, okay? And I'll show you why in a second, okay? So essentially what we've done is we've changed the space that we're operating on from product space to characteristic space. So why is this an advantage? It's going to get rid of some but not all of the problems, okay? What we usually say is the new space typically has much smaller dimension than J, okay? So I can summarize the taste for a product by K characteristics, okay, where K is much smaller than J. So for example, we're doing autos, and we thought that there's a preference for each character. Let's just say it's linear, and there's a preference for each character. So there's a preference for price, there's a preference for car size, there's a preference for SUV, et cetera, okay? Say we had 5 of those characteristics. That's probably not enough, but say we had 5, and we assume the distribution of those preferences was normal, okay? So you'd have 5 means, and then you'd have the variance-covariance matrix, which would be 6 times 5 divided by 2, works out 15. That gives you 20 parameters to estimate, okay? And you can get all 50 times 50 cross-price elasticities from those 20 parameters. Is that clear? That's what gets rid of the too many parameter problem, okay? So, so that's the too many parameter problem, and I'll come back to, there's problems associated with that. We're not going to get rid of all the problems. I'll come back to the problems in a second, okay? Now, the second problem with characteristics basically for I/O was this inability to get demand for new products, if you recall, okay? But now we have an estimated demand system. It's on characteristic space, okay? So now I put in another good with a different tuple of characteristics. Is that clear? And I just ask what persons will buy when against all these goods, including the new good, okay? So again, there are going to be problems with that, but in principle at least, it's doable, okay? We have a chance, okay? All the literature starts with a guy named Kelvin Lancaster, and then Dan McFadden started the econometrics of this, okay? So there was also this extensive related literature in I/O, which was really literature about product placement. So if you read Tirole about where are we going to place new products, it'll be models like this in characteristics. Hoteling, right? There are people on a beach on one characteristic is where the guy sells ice cream, and the other characteristic is where you are. Okay, and that's really just a characteristic model. We'll return to that in a second. So there's been a lot of literature on this. Okay. So the two problems we had before are going to reappear here in slightly different form. And it's because they appear in slightly different form that sometimes we can get around them. Okay? So again, if there are a lot of characteristics, you're back into the too many parameter problem. Is that clear? The whole problem would be if I had 50 characteristics, I'm back to where I was before. Okay? Typically, by the way, producer goods have really a very small amount of characteristics you have to keep track of. So if you think of computer chips, you need to know, the speed, CPU, maybe reliability, maybe size of chip. And you'll get, if you do R squares of quantity and price on that, you'll get R squares, about 0.95 and 0.98. Okay? Where it's not quite true is in consumer goods. Okay? Because if you really thought about a car and the differences between different cars, there's 5,000 characteristics. You could put in the leather in the seats, the color of the car, and everything else. Okay? So we're not going to be able to put in every characteristic that matters. Okay? We're going to put in what we think are the major characteristics, but then we're going to allow for an unobservable characteristics, which picks up all the little things, okay, that we didn't pick up in the observable characteristics. Is that clear? Okay. So this unobservable characteristic is going to end up being a little bit of a problem, okay, because there are all these little things. So it's not so true anymore, but a Mercury used to look just like a Lincoln. If you did all the standard, car size, seats, everything, they look just like a Lincoln. What the Lincoln had was a lot of little doodads that made people want it, okay, and Lincoln priced to it, okay. So the price of the Lincoln was more than the price of the Mercury because of all the little things that go into this unobservable, okay? So once we allow for that, we're going to have a price endogeneity problem. There's going to be price on the right-hand side, and then there's going to be this unobservable characteristic which is correlated with price. Is that clear? Just like you have in standard demand analysis. The problem here is it's going to be in discrete choice analysis, is it's going to be buried inside, as Aviv will show you next lecture, it's going to be buried inside a nonlinear function because it's discrete choice. So it'll be the probability of some event, which has got to be nonlinear because it's got to be between 0 and 1. Is that clear? And standard things that you've been taught don't teach you how to do nonlinear instrumental variables. Okay, so we need a solution to that problem, and that's one of the things BOP will bring in. Okay? So that's the too many characteristic problem. On the new good issue, you have to be quite careful. Okay, so you'll do a reasonable job on goods whose characteristics of the new good are similar to the goods that are already sold. Okay, they're somehow spanned by the characteristics of the goods that are already sold. So my favorite example of this, if you try and do it for goods that aren't, that are out of the characteristic space, you're going to do terribly, okay? Because it's all just a projection, okay? And typically very new goods, the reason they're very new goods is because they found another dimension. So my favorite example of this is the desktop and the laptop, okay? So if you would have figured out, before anybody put in a laptop, okay, you would have tried to figure out, what will the demand be for the laptop at different prices, okay? So the characteristics of the desktop that typically went in are, were memory, speed, and resolution of the screen, maybe. Okay, and all of those were better on the desktops than on the laptops when they introduced the laptop. Okay, and the laptop had a higher price when it was. So you would predict zero demand for the laptop. Okay, and it's because even if you had what's different about the laptop, the size and the weight. Even if you had size and weight of the desktops, it's just so much out of the space of the size and weight of it that it's all a projection, and the projection would have went haywire. Okay, so you have to be a little bit careful when you're doing new goods. People who make real money on real new goods, it's because they think of something that really is out of the space of things that we know how to do. Okay, so now I'm going to become a little more technical, okay, and just start you off, and then Aviv will come in. Okay. So I'm going to start with a model of a consumer choosing at most one of a finite set of goods. By the way, well, I'll come back to this. Okay. So I'm going to define a product as a bundle of characteristics, which include this unobservable characteristic. Okay. I'm going to assume preferences are defined directly on those characteristics. Okay. And then I'm going to assume that each consumer chooses the bundle, at least until the last lecture. I'm going to assume each consumer chooses the bundle that maximizes its utility. Okay. It's only going to be one good. Okay. And it's going to choose the bundle that maximizes the utility. Consumers are going to have different preferences over these characteristics, so different consumers are going to do different things, okay? And those preferences are going to be related to the characteristics of the consumer, okay? Some of which might be observed and some of which might be unobserved, okay? And the way I'm going to get aggregate demand is I'm going to just have this utility function for each consumer as a function of theta, this parameter vector, which tells me the interactions, how much a person of this income group dislikes price versus some other income group dislikes price, or family size likes car size, or whatever you think the relevant interactions are. So those thetas are going to determine how important those things are. Okay? So I'm going to say fix theta, okay? And let every consumer choose his maximum if that were the true theta. Is that clear? That's going to get me a demand for each consumer. And if I'm going just to aggregate data, I aggregate over the types of consumers to get aggregate demand. Is that clear? That gives me the model's prediction for demand, conditional on theta. I know what demand was. I find the value of theta that makes the model's prediction as close as possible to the data. That works out to be consistent and asymptotically normal. Okay? So that's the model. By the way, all economic models, no matter what anybody tells you, they're that. There's a model conditional on a parameter vector, okay? And then there's data, and you find the parameter vector that makes the model, the predictions of the model as close as possible to data. That's what's going on when you do generalized method of models. Okay, so now I'm just going to make that a little bit more formal. Okay, so the utility of the individual I for good j is going to depend on xj, which are the characteristics of the product, okay, and pj, which is the price of the product. So price is just another characteristic. We generally treat it differently because when we're doing equilibrium calculations, price will respond, and we'll assume, at least statically, that the x's are fixed. So the products have given characteristics, but the managers of the products can change price in response to environmental change. Is that clear? Whereas it takes time to change the characteristics. So if we're not doing, but if we were doing dynamic models, we'd also endogenize the characteristics. That's the difference between the dynamic model and the static model. Okay? Okay, so xj are the characteristics, pj are the price, and nu I are the individual attributes. So they were zi before. I should have kept zi probably, but nu I is in the literature. Okay, so I'm going to use nu I. Okay? And this is going to be, there's going to be j inside products and one outside product. Is that clear? Okay. So the j inside products are the products that are actually competing in the market. So they're the cars that are competing in the market. And the outside product is what you do when you don't buy any car in the market. Is that clear? Okay. So it's a fictional thing. Okay. We don't really, and often it's modeled as the utility of the income after I pay the price of the car or the price of the good. Okay, what's the utility of that income? Okay, it's important for several reasons, keeping the outside good. It's the only thing sort of fictional in the model. If we didn't have an outside good, we couldn't model aggregate demand, which is because everybody'd always be purchasing everything. Okay, and I need people moving on the extensive margin. Okay, so I couldn't model aggregate demand. Also, if I didn't have the outside good, okay, I'm not analyzing a random sample of consumers. I'm analyzing a sample of consumers that did purchase a car. And they're going to be different from the random sample of consumer in the CPS or otherwise, okay? And I'd have to take account of that in the estimation algorithm, okay? And finally, it would be very hard to analyze, questions are fine. If I didn't have an outside good, it would be very hard to analyze the benefit of new goods, because much of the benefits of new goods are drawing people in who weren't purchasing a good before, and now there's a good that they like enough to purchase. Okay? So for all those reasons, we keep the outside good in the analysis almost always. Okay? So the product characteristics, of course, are constant across consumers. Okay? So now we want to know what's the demand for product J. Well, the demand for product A, remember everybody has this utility function back here, conditional on theta, okay? And the demand for product J are just fix that theta. How many people have uij greater than all the other uik's for that theta? Okay? So you fix theta, that means you fix everybody's utility, okay, conditional on their characteristics. There are going to be some people where uij is greater than all the rest of the uik. Those are the people who are going to buy uij. Okay? So formally what you do is you find the set of these news, and then you just find the density of people who are in that set. You just find the number of people who are in the set. You just sum up over the people who are in that set. Okay? That gives you the prediction of the model for the share of good J, given x. Now, when there's x without a subscript, it's the whole vector of x's, one for each product. And the vector of p's, that gives you the prediction from the model. Okay? And then what Aviv is going to tell you how to do is fit that prediction to the actual data. You have the data on the shares, okay? And you just fit the prediction to the data. You find the theta that fits the best. And there are different ways of doing that. Okay? If you wanted total aggregate demand, you'd have to multiply the shares by the size of the market, which is capital M. Okay? Okay, so some details. Okay, so this utility function is only cardinal. Okay, that is, I can multiply, it's invariant to what's called affine transformations. I can multiply it by a positive, for each individual now, I could multiply all the utilities of that individual by a positive constant, okay? And I could add a constant, negative or positive, to each of the utilities, and it wouldn't change his choices. Because all that matters is the ordering. Is that clear? That, in econometric terminology, that means I have two normalizations to make. Okay? So the way they're usually made is I set the utility of the outside good to 0. So that's like saying I'm subtracting the utility of the outside good from each of the inside goods. Is that clear? Okay. That has implications, by the way. That's not, okay? And usually what happens is there's an error term in the utility function, and the coefficient of the error term becomes 1. That's the positive normalization. That's the positive constant. Okay? So you got to be a little bit careful, by the way, because now you're estimating the utility for good J. Okay? Say you're estimating for a car. Okay? So you're not really estimating it for a car now. You're estimating the difference between the car and the outside good. So if the outside good is the means of transportation to work, okay, and you're in New York, it's very different than when you're in Framingham. Is that clear? And so you got to understand that what this uij is now is really uij minus ui0, and that has an implication for how you model what's going on. Okay? Okay. So here's some simple examples, and then we're gonna finish this one on time. The other ones we might not. The simplest, there are two models that arose in I/O all the time. One was this simple horizontal model, people on a beach. So we're going to generalize from these, but let me give you where we're starting from. There are people on a beach, and ice cream vendors on the beach. Okay, delta J is the location of the ice cream vendor. Nu I is your location, and then you don't like price. Okay, so this is a model with two characteristics, product characteristics. The location of the ice cream and price. Okay, and and in this particular model, characteristics are called horizontal because different people, because they're in different locations, like different products differentially. There's not common ordering of products. Okay, depending on whether I'm close to the product or not, I'll like it more or less. Okay. Whoops. So these are typically called horizontal characteristics, where there isn't a common ordering of products. We don't all agree on the order of products. Okay. The alternative is the vertical characteristic model. So there, the characteristics is delta J, and we all agree on it. Okay? So we all agree that one good is better than another good. The difference between us is that we have different coefficients on price. We have different incomes or different wealth, and we care about price differentially. You have a free normalization, right? So this nu I really is just the ratio of how much you care about quality to the ratio of how much you care about price. Okay, because I can multiply everything. I just normalize this to be 1. Okay? So that's the other one that appears in I/O, and I'm going to tell you the generalization story. The other one you've probably seen is the Logit model. Okay? So the Logit model just says Uij is delta j, which might be a quality minus price if you like, and then these epsilon ij's. Okay? So the intuition is there's a mean utility, and then there's differences across individuals of the utility for this particular good. Okay? The reason you've heard about the Logit model is because it has two nice features. Okay? Those epsilons, by the way, they have to be, for the general model, without the Logit assumptions, those epsilons have to be independent across individuals for a given product. So I look at the epsilons across individuals for a given product, they're independent. I look at the epsilons across products for a given individual, they also have to be independent. Okay? Okay. You're going to see those are the bad assumptions. Okay? But if it also has this functional form, which is extreme value type 2, okay, it has these wonderful magical properties, which are the probability of the maximum being a good has a closed form, and we will show you what that is shortly. Okay? So I can tell you what the probability is of choosing good j. Okay, without ever doing an integral over the epsilons. Is that clear? Just I know the functional form for it. Okay? And moreover, I can tell you the expected utility given these deltas. It's the expected welfare of the agent given the deltas. Okay? The Daly-Zacharias theorem. So these are the two properties of Logits. They're the only distribution that I've ever seen. I think there's a proof that they're the only one that exists that have these two properties. Okay? So why do I want, remember, for each individual, everybody with me? Okay? The probabilities of what he's going to choose is just the probability that delta j is the max. So if I wanted to form a likelihood or a moment based on that, I need that probability. Okay? And this is telling you that that probability has this nice analytic form. Is that clear? I don't have to do any integrals. I can get it exactly right. Is that clear? Okay. So before you had computers, this was an invaluable asset. Okay, because you couldn't do it any other way. Okay? Similarly for the expected utility. So the thing that you should realize about this, and we're going to come back to it in different ways, is this model implies that no matter what good you chose good j, your preferences over other goods are the same as anybody else's, because it's an IID epsilon. Take out one good, is that clear? It's got the epsilons of that good have no relationship to the other goods, epsilons. Is that clear? This is called the independence of relevant alternative assumption, or IIA. I'm sure you've heard about it. It has very many bad properties. Okay, if you think of what's going to go on, you increase the price of a car, a big car. Is that clear? So you think that some people will leave the big car. You think the people that will leave the big car will go to other big cars. Is that clear? The reason they bought the car in the first place is they wanted a big car. Is that clear? That can't happen in the Logit. Okay? It's, as I say to my students, if it does happen, you have a computer programming error. Okay? It can't happen. I mean, mathematically, it can't happen. Okay? So those are the things we want to get rid of. Okay? Those kind of things. So, whoops, wrong page. Okay. So let me show you just how bad these are before, and then show you the generalizations, and then Aviv can tell you how to handle the generalizations, okay? So I'm going to think of two. I could have done the horizontal model. It's very similar. So I'm going to do the vertical model, okay? So assume we were doing the vertical model, and we're going to try and take that to data, okay? So there's one character. We all believe it. We all agree that in the ordering of goods, okay? And the price of j, we want to estimate the deltas and maybe the distribution of the impact of the distribution of the news. Okay? So what's going to happen in this model? So what's going to happen in this model is if I order the goods by their quality, I have to order them by their price. Because we all agree on quality, and nobody's going to buy a lower quality good at a higher price. So the order of quality is exactly equal to the order of price. Is that clear? So that's going to have to be in the model. Okay? So now consider what happens. There's the jth good, okay? And let's see what happens when we do something like increase the price of the jth good, okay? So we've ordered the people, so their j goods are increasing in quality. People with a lower nu I, with least aversion to price, buy the highest quality good, okay? That's the only difference between people is these nu I's, okay? And they'll buy the highest quality good and so on, okay? So what's going to happen is I'm going to have the people who buy good j, okay? And there's going to be a bunch of people who are almost indifferent between buying good J and the one of slightly higher quality, J plus 1. And there's going to be some people who buy good J who are almost indifferent between the lower quality, good J minus 1. Okay? So now I'm going to increase the price of good J. Okay? The only people who can move are the people who bought good J, because everybody else is just better. You know, they were better off before. Now the price of good J is gone. Okay. So the only people who move are the good that buy, and the people who move will be the people on the margins that were indifferent before. Okay. So now the price of good J went up. The guys that were just on the margin of buying good J plus 1 will probably move to J plus 1, and the guys who are just on the margin of J minus 1 will move to J minus 1. But the only people who move are the people of J, and they only move to J plus 1 or J minus 1. Okay. So again, this is just an implication of the model. It can't be, the model won't allow anything else to happen. Okay. So if you consider like the auto market, which Aviv is going to go into more detail on. So you just line the cars up by price. Okay. And say we got the Ford Explorer, which, if you don't know, is an SUV, okay, was a neighbor in price space to the Mini Cooper S, which is approximately right, okay? And then the next neighbor is the GM sport utility vehicle, okay? So I'm going to increase the price of the Ford Explorer. The model is going to say that people can go to the Mini Cooper S, but nobody will substitute to the GM SUV, okay? It's impossible. Okay, it can't happen. Okay. Similarly, if you think about so the elasticity with respect to price, and remember, elasticities in IO, we're going to come back to this. They determine markups, right? Because you have price. If you look at simple Nash formula, this price equals marginal cost, okay, plus a markup, and the markup is 1 over the semi-elasticity of demand. Okay. So the elasticities in this model are going to be determined by the density of people on the margin. Because if I increase the price and there's a lot of people just on the margin, there'll be a lot of people who move over. Okay, is that clear? So you're going to have, if you had a symmetric distribution, okay, so for example, in the coefficient of price, okay, which we think is usually round right, okay, so the people at the elasticity on one side will be exactly equal to the opposite side's elasticity, because the densities are going to be the same in a symmetric distribution. Is that clear? So the people who have very high aversion to price are going to have the same elasticity as the people who have very low aversion to price by construction. Okay? And if you take that to the economics of the problem, it means the people who buy high-price cars, the markup on the high-price cars, are going to be exactly the same as the markup of the people on that were buying the low-price car. Okay, and we know that's crazy. Okay, it's crazy for it's crazy in the data, but it's also crazy for good reason, because high-priced cars have high sunk costs, and they have to have high markups just to justify the sunk costs. Okay, if nothing else. Okay, so those things have to happen in the vertical model. Okay. So that's what's wrong with those kind of models. Okay, and now the Logit models. I'm going to tell you what goes wrong with the Logit models. I'm going to give you the 2 generalizations, then I'm going to hand it over to Aviv. Okay, so the Logit model, the closed form for the probability is just exponent delta minus p over 1 plus the sum of the exponents. So you can go and prove that. It's about a page of interchanging variables and formulas, and every time I do it, it takes me a day to do it. But it's true. Okay, that's the answer. Okay, okay. So these are the analytic forms. Okay, so this implies that if you just work it out, the derivative of good J with respect to the price of good Q, okay, is going to be Sj, Sk, or with respect to the price of good K, is going to always be Sj, Sk. Is that clear? So 2 cars with the same share have to have the same cross-price elasticity with every other car. The model will not allow anything else to happen. Is that clear? So, the example we used in the paper, I think, is the paper was written when the Yugo was in for a while. The Yugo was a Yugoslavian car which was only in the market for 1 or 2 years. It was a lousy car. It had a very small price, and it had a very small share. It was a lousy car, but it had a very small price. It was enough to induce certain people to buy it. Okay? It had almost identical shares to the high-end Mercedes. Okay, because the high-end Mercedes cost $90,000, very few people, but it was supposed to be a very good car. Is that clear? So this says that when you increase the price of Yugo, people go to different places. And you increase the price of the Mercedes, people go to different places, and they're going to go in exactly the same proportions. Is that clear? Okay, which is crazy. It also implies that if we had a Nashian prices equilibrium, single product Nashian price equilibrium, they have to have exactly the same markups. So everybody knows that the markup on the Mercedes is greater than the whole price of the Yugo. Okay, so people, it just didn't make any sense. The ohm price derivative is S1 minus S, and that's the reason that things with the same price have to have the same markup, because the ohm price derivative is the elasticity. Okay, and again, no data will ever change this. Okay, if you get a computer program which tells you, you use a Logit, tells you it's different from this, you got a bug in the computer program. Okay, it can't happen. Okay? Okay, so here's the generalizations, and this is what we're going to work with at least until the last 2 lectures tomorrow. Okay, where we're going to go into newer things. Okay, the first generalization I'm going to call generalization 1 is what Anderson, De Palma, and Thies in their book on the theory of this stuff called an ideal type model, and Steve Berry and I call the pure characteristic model. So all it does, okay, is it generalizes on both the horizontal and the vertical model. It allows for multiple characteristics, some of which can be horizontal and some of which can be vertical. Okay, so it looks like this. It just says, look, an agent with characteristics nu I, which is a vector, preference for goods is he has a separate preference for each good. And it might actually depend on many nus. It might depend on his income for each characteristic. It might depend on his income, his demographics, and everything else. Okay? So we have a bunch of things which determine my preference for each characteristic, and then we have many characteristics. Okay? So the preferences can be horizontal or vertical on each characteristic. Okay? And you're supposed to estimate the thetas. Okay, so this is, for obvious reasons, a pure characteristic model. Okay? The characteristics of individuals interact with characteristics of products. Okay, that's what's going on. Okay, you can show, by the way, that the ideal type model that theorists use, which is this one, there's an ideal type for me, which is xjk, which is nu ik, and then there's characteristics of the products, which are xjk. The ideal type model is exactly the uij model up above after you do appropriate normalizations. So this is just the theory version of it. Everybody has an ideal type. Okay, we have a metric of how far I am away from the ideal type, okay, and that's what the pure characteristic model is. Okay, the difference, okay, so let me now just say, that's the pure characteristic model. BLP is identical, except for one thing, okay? It adds an epsilon ij. And these are going to be type 2 extreme value, the same thing that was used in the Logit. Okay? Now, however, there's a difference. Okay? Because what's going on is now I increase the price of good J. Very particular people leave good J. Those are the people who like the characteristics. The people who bought good J, is that clear? Are the people who like the characteristics of good J. Okay? And because of the new ij, they're going to move to other products with the similar characteristics. Okay? Because each individual has a new I, so he likes different characteristics differentially. He bought this car. Okay, some people will leave because the price of that car go up, but their preferences for characteristic are constant, so they're going to move to similar kinds of cars. Okay, and that breaks the IIA property, the independence of relevant alternative property. Okay, because if I'm in this kind of car, I like cars that are of these characteristics. Okay, if I bought this kind of car, that's because I like cars of this kind of characteristics. Okay, and when I go to look at the other cars, they're going to be cars like that. Okay? Okay, so it breaks it. Let me now talk a little bit about the difference between the pure characteristic model and BLP just for a second. The only difference between these is the epsilon ij's, okay? So you can show, you might well think this, you can show that the pure characteristic model is a limiting case of BLP. So it's not a special case. This actually difference matters, okay? The way you can show that is just put a sigma on this and normalize something else. You always have to normalize one thing. Here the normalization is on the epsilon ij. It has a coefficient of 1, okay? Put a sigma on the epsilon ij and normalize something else, and take that sigma to 0, okay? And in the limit, you'll get BLP. You'll get the pure characteristic model, okay? Why am I telling you this? Okay, why do I bring up the pure characteristic model at all? Okay, because BLP has problems, and for some kinds of markets, and the problems are related to the epsilon ij's. the presence of the epsilon ij's. Okay? So the epsilon ij's, so when you think of unobservable things, okay, that are affecting demand, they're either individual characteristics that are unobservable or product characteristics that are unobservable. You know, they're not just from anywhere. Is that clear? Okay. So if they're individual characteristics that are unobservable, okay, they're going to be correlated across products. Okay? And if they're product characteristics that are unobservable, they're going to be correlated across individuals. Okay? So you think that the epsilon ij, it's iffy if they should be there. Okay? And the real reason they're there is computational, which has nothing to do with economics. Is that clear? So you might want to get rid of them. Okay? And if you got rid of them, you'd be back at the pure characteristic model. Is that clear? Okay. So the reason I say it's a limiting case is because it works out that it's very hard. So if you really did have a sigma up here and you divided by sigma and let that sigma go to 0, which is the way you do the proof, okay, you get coefficients who are very large, right? Because everything else is going to blow up. You're going to divide by something going to 0. Is that clear? And computers can't handle that. Okay? So they will not. So if you had, for example, if you really believe the real world was pure characteristic world, and you estimate BLP, you'd think, well, you know, if it was pure characteristic, maybe it would replicate the pure characteristic model by just getting a sigma which was small enough. Is that clear? But the computers won't do that. It doesn't do that very well, because you'd need a sigma that's you'd need to evaluate numbers which are too large for a computer to handle. Okay? So the question is, when is this problematic? Okay, so there are two cases where it can be problematic. Okay? What happens with the logit errors, okay, is they have, you know, they can go off to infinity and negative minus. They have what's called full support. Okay? So if you put in another good, okay, and even if it's very close to the goods that are already in, okay, somebody is going to like that good infinitely more by the model, because the epsilons, some guy's going to draw an independent epsilon that's way out there. Okay? And that's going to limit cross-price elasticities. There's a lower, you cannot put goods close enough to get their cross-price elasticity very high, too high. It's impossible. There's a lower bound to it. Okay? Now again, it's only, we've done a bunch of simulations on this, and it only ends up being real problematic when you have a lot of products and some of them are very, very close to each other. Is that clear? Usually BLP does pretty well, even if the real model is pure characteristics, which is the Monte Carlo that we did. The Monte Carlo that's been done on this is you assume the real data is a pure characteristic model, you estimate BLP, and you see how bad you do. Okay? And the only time you really do badly are when there's really lots of goods very close to each other. Okay? You can ask whether that will ever happen or not. But if it does happen, you can have problems with BLP. Similarly, for welfare, you can have problems. So you might ask, okay, and again, you might want to go to the pure characteristic model. That model ends up, without not approximating, just straight going there, that model ends up being hard to estimate, okay? Just hard to compute, okay? So people are starting to use it now. Aviv's going to tell you how to compute BLP in a second, okay? It's much harder to compute the pure characteristic model, okay? Though with new advanced techniques, it's being computed by by a number of people, okay? I've been using the pure characteristic model. For most part, though, the reason you see BLP is because it's easy to use rather than the pure characteristic model. Is that clear? And for most markets where we've analyzed, it doesn't make much difference. Okay? So I'm going to stop here, and now Aviv's going to tell you how to do BLP. We're taking a break first. Yeah, Darren. Yeah. Right.
Now, why is it, people have probably given thought to other ways of just having a giant error term than having the covariance matrix that's parameterized by the underlying distributions of the x's and the parameters. And the question is there an alternative to this? Because this doesn't pose
strict
linear structure.
Right. The linearity doesn't matter, but it's going to impose small number of the covariance is going to be a small number of. So let me just tell you what Dennis just asked. Let me reinterpret it, okay? You could say, let's just let it be delta J, and then have a full variance covariance matrix of errors. Is that clear? BLP is a special case of that. Not quite, because I can have observable things, but if I only had unobservable characteristics, if I didn't have micro data, which matched individuals to what, I would have exactly what Dennis said. I have a variance covariance matrix, okay? The variance covariance matrix has J times J plus 1 divided by 2 parameters, which is back to the J squared problem. Is that clear? Okay, so then the question is, how do you structure it? And what this is doing is structuring it. It's saying people have different utilities for different characteristics, okay? And that's what's generating the covariance across the products and much of the cross price losses. So, for example, if you don't have the right characteristics in there, okay, and you don't load it, then you're not going to get the right substitution patterns for exactly that reason. But the structure that's being imposed here is from a statistical point of view, is the structure of the covariance matrix derives from preferences on these characteristics. That's what's going on from a statistical point of view. But that's what we're doing.
I know.
That's exactly what we're doing. Right? So, I mean, I'm not saying it's the only way of doing it, okay, but that's exactly what we're doing. We're letting it feed through the characteristics of the product. That's going to structure the covariance matrix, and that's what's going to reduce the dimension from J to J plus 1 to K plus 1. That's exactly what we're doing. Nothing more than that.
Yeah, no, I was just asking if you experiment with alternative parameterizations.
You're going to see some of them. I mean, Aviv will go over something like nested load, which is a special case of this. Okay, and you'll see there are problems that people run into with it.
The other question, could you just expand further on something you said, which is, it always bothered me when you put in the zero of the alternative good, the outside good.
Yeah.
As you pointed out, the outside good differs across cities, even the inside good differs.
Right. Yeah.
Can you talk about that in a few sentences of paragraph?
It depends. I think you want to, so if it's cars and you're worried about travel to work, you really want to know if there's a subway system, what's the other ways of getting to work from this place. You know, in principle, what you'd like to also know, by the way, is what the second car holdings is of the person, which puts you into a whole another set of problems, but because the second car holdings would correlated with the preferences for the first car holdings. But you definitely want to know things like that, and that might differ between cities. So the UI 0 would be different between different markets. No, but what you would do, right. So what you would try and do is you would try and get the characteristics to determine the outside good. That's what we did in BLP, and put it back in the model. So the utility of good J depends on the characteristic of good J and the characteristic of the outside alternative. And you would estimate them jointly. And the characteristic of the outside alternative would vary across markets. That's what you'd try and do. And that's the logic of it.